Okay, so welcome. This is our first in-person event since February. Gosh, when was it? 2020. Our March 2020 was cancelled because that's when it all kicked off. And then we had our first Zoom talk in April 2020. So we've been Zooming ever since. Pete's here. Pete Richardson is our speaker this evening. He's come all the way from Bleedon near Weston-super-Mare to be with us tonight to talk about his telescope project. And the members of the audience can see the telescope there. So there's no big reveal. The big thing is actually here. So for those at home, I'm not sure I can actually, let's try this out. There you go. That's the beast that we'll be talking about tonight. But we'll on to club matters first. So welcome back, everyone. It's great to see so both people at home and here in the museum. It's nice to be back, to see faces, and hopefully soon, if I actually predict some clear weather, to actually do some observing together. But I think the run is 5 missed. So I've had 5 events so far in a row, which have all been cancelled due to weather. So maybe number 6 is going to be the one that's going to happen. We're currently 54 members, and your organising team is Chris, I've got Jonathan, Mike, and myself. Abby, she has a new job. She has moved to north, not that far north actually, but she's gone to pastures new, and she's joining Astro Societies up there. So wish her the best, but it does mean she stepped away from the committee and she left us to our own devices. So good luck to us. With that in mind, the coordination team or committee, whatever you like to call them, is actually up for re-election in November. So you can put your name forward to be chair, an ordinary officer, a secretary, a treasurer. Chair, secretary, and treasurer have things to do. Ordinary officers just help out where they feel fit, and that's what Abby was doing. And I think she enjoyed it a great deal. She was with us for oh gosh, I can't remember how long now, a year and a half or a year, picking up activities. Let's see. So most people, if you really want to help out, then an ordinary officer is kind of a good role to be in. If you've got the time of a particular month, you can pick up an action and run with it. If you haven't the next month, then you can just skip that particular month. So that's quite a good role. But I've been chair for 2 years now. Some people may say that's too long. So if you want to be chair, put your name forward. Secretary is Jonathan currently, and treasurer is Chris. All 3 of us are currently deciding whether we're going to put our names forward. So it is a fair vote. So that if you do want to put your name forward, everyone will have a fair sort of what's the phrase? Brain's gone dead.
Crack of the whip.
Crack of the whip. Yes. Okay, but please, because essentially it's the people in here who actually do the behind the scenes organising. So the fewer people we have in the coordination team, the more work they have to do, the more tired they get. Right? So the more people on the coordination team, the better. So please have a really good positive think about what you might like to do if you can spare us a little bit of time. Since the summer, we've still been pumping out our newsletters. No one's given us any feedback, so I think we're doing the right thing. We'll find out. And we've just thrown out the October one as well. And hopefully what I'm asking is, so we've got little spotlight articles in there, so little things about what kind of astronomer are you, when did you first pick up a telescope, all those kind of things. And in each one, I've tried to see if one of the members would like to contribute an article. And for his sins, Steve Kimmins has purchased a unistellar EV scope. That's one of those fully computerized, no eyepiece telescopes that takes lovely pictures. And so you probably read his review on the EV scope there. Okay, so we'll keep doing that. And if there's anything you want in particular, then just let us know. If you want to submit an article, then let us know. I will pick on people. I'll send them an email saying, "Ooh, you were talking about something interesting the other week. Would you mind writing a little article about it?" So hopefully, if you do so, don't feel upset that you're being picked on. You are special because I did think of you, but I will be asking other people as well. So just to balance it off. Okay. And we've also been busy with the last, beginning of September, we did 2 shows. We went to Bathampton and we went to Wellow, their 2 fairs. And so We entertained the families and their kids, and met some astronomers, some secret astronomers hidden around, people with telescopes and cupboards and things like that. So hopefully a few of those will be thinking about digging them out. And we had good help from lots of people. So we had Sandy, Prim, Roger was there, Tony was there, I was there, Steve Kimmins was there. Who have I forgotten? Who have I forgotten? Roger, I've got you there. Yeah. Sterling effort by Roger, he came to both. So that was great. And we probably saw a couple of hundred people to sort of inspire. And we've had at least 2 school contacts because of this. 1 membership and 2 school contacts. So just for being out there, it's worthwhile, but it does mean that our outreach program is benefiting from this as well. So that's great. And talking about outreach, actually South Down Scouts also contacted us on the back of one of the things. They saw us at Wellow. And so we've got a visit to South Down Scouts on the 11th. Monkton's Coombe School, we inaugurated the observatory with the teachers 2 or 3 weeks back. And the Astronomy Club is actually officially starting on the 13th of October, based at the observatory. So that's great news. That's now an asset to the school. The mysterious things, because we've got a 12-volt solar system in there. We were trying to work out solar voltaics battery system, not a solar system with the sun and planets and things. That's too crazy. And we couldn't work out why the battery voltage was dropping in the entire system. We went in there and visited, and the battery voltage was down. Oh, no, not the voltage, the amperage or whatever it is, the capacity of the batteries was down. And we later found out that the school's been using it for rocket launching. They've been pumping up water bottles and barrels and firing them out, and for physics experiments. So not only is it an asset for the school in terms of astronomy, they're also using it for physics and extended by using us as a power source. So that's really good that it's getting that use. We've got school visits to St. Philip's and St. John's in October and November respectively, and both Exmoor Dark Skies and Marlborough Dark Skies have asked us along to their festivals. So we're running sessions there. Exmoor, I'm actually co-running a session with Pete's wife, Jo from Space Detectives, and at Marlborough we'll be doing, oh gosh, a workshop, a talk, and we'll be doing observing as well in the evening. So if anyone sees me at the end of the day on the 30th of October, I think I'm going to be ragged, but we'll have to see. 13th of November, Bristol, Bath and Cardiff Astronomical Societies, all 3 astronomical societies, have got 4 speakers talking about extrastellar environments. So someone talking about neutron stars, someone talking about supernova, and I can't remember what the other topics are. I should do. Black holes, probably one of them. So we've all ganged together. We've gone to the universities and said, does someone want to do a talk? Someone want to do a talk. And so that's actually going to occur online on the 13th of November. As sort of a get together of different things. I think Dr. Robert Massey is going to host it as well. So that'll be an online event that we're part of the 3 that have organised it. When I say part of the 3, all I've done is I've badgered Bath, University of Bath, to try and get some speakers, and I failed miserably, even Carol Mundell, but because I helped with the badgering, we get equal billing to everyone else. They are indeed. And then the really big one, we've got the Museum of the Moon coming to Bath Abbey from the 21st to the 20th of December. And that's where we're going to be doing Sunday night and Monday nights, actually, in the evenings when the Abbey's open and people are walking around. We can sort of say, this bit of the moon, that bit of the moon, that's quite interesting, whatever. Or just stand back and just let people sort of take in the thing. And if they want to ask a question, they can come to us to ask a question, or sort of say, wow, that's interesting. And then you can tell them why it's interesting. So hopefully I'll make things a little more fun for the visitors to the Abbey, especially since they've now cancelled the Christmas market. So we were thinking that we're actually going to get a lot of trade coming in from the Christmas market. Now there's nothing else to do. We might get trade that way. So it might not actually have an effect on us in terms of people coming in. So for those that have volunteered already, there's a visit, a tour of the Abbey next on the 6th. So when's that? Next Wednesday. Yeah, next Wednesday at I think it's 7 o'clock, but I'll send a note out as a reminder, which will turn up to the Abbey doors, and then we'll be taken around and we'll be taken up to the top of the Abbey, where hopefully we'll have a chance to see what kind of astronomy you can actually do, because I've only been up during the day and I haven't seen the amount of light pollution that there is from there. So fingers crossed it's doable. But if not, we'll all be down around the globe for sort of like 2 or 3 people of an evening, just helping the visitors out in terms of just guiding them and sort of making their experience of the moon even more enjoyable. I've put down these as shared observing events. So this coming weekend, so I'm going to cross my fingers that actually happens. If it does, we'll do it at the observatory at Monkton Combe. So we'll sort of bring your own scopes, as well as potentially trying to see if we can hang off the end of the Victorian scope as well. But whichever one. So fingers crossed. The weather forecast so far was no, but you never know, weather forecasts can change. And we're suggesting so that the coordination team just had a chat, perhaps if we change venue a little bit, rather than just always going to Wellow, that might make it a bit more fun. But that's going to be a bit flexible. Let's see how it runs and see how that idea plays out. Going forward, our gathering in October on the 27th, we'll have Professor Lucy Green giving us a talk on latest solar research. I couldn't get any more from her agent other than that byline. So hopefully in the next 4 weeks, I'll actually manage to touch base and get a sort of a topic and abstract. But effectively, she's in the forefront of solar research, based at Mullard Space Labs, or she works with them as part of the University College of London, developing new sensors and things. So was it Solar Orbiter is the one that she's currently getting lots of results and information from. So that should be a very interesting talk. But I have talked way too long already. So building a 10-inch dob for practice. So I introduce you formally to Pete Richardson. I've known him for quite a while now. We've been to astro fairs and things like that. But a few years ago, Pete said he had an intention to make his own telescope. And Pete, you were from Jordan F1 team. You were composite manufacturing manager. Yeah. So that's quite high tech. Yeah. And then you moved into Airbus to test their wings, to see if you could break Airbus wings. Yeah. Yeah. So you're doing that currently. Still there, yeah. So tolerances and fine engineering, precision engineering is your bag, really, isn't it? Hopefully. Yeah. So when we turn to making you, or you going to build a telescope, it's not going to be just any ordinary telescope, is it?
It's not what I set out to do. No, I set out to make it as exact as I could, and obviously the mirror being the most important part. Precision engineering. If I can do it, that was the challenge I set myself.
Excellent. And as you can see, for those people there, and I'll turn the camera around in a second so you actually see it, the telescope, the finished 10-inch telescope is actually with us tonight. It has a blank as in the mirror because juggling a high precision ground through many, many hours of perspiration and frustration, bringing that down here and accidentally getting damaged is something we didn't want to do, didn't want to risk. So it's actually got an ordinary glass blank in the bottom of it, but every other part of the telescope is here and present tonight. Okay, what I'll do now is I will just flip over onto, so I'll stop the share, I'll just flip onto the presentation that Pete has for us this evening. And so just bear with me. And almost there for you. And I think it's that one on the screen. Go. Can everyone see the full screen design and build of a 10-inch truss dobsonian? Chris, can you see that okay?
No, all I can see is
you're seeing the notes screen?
I'm not seeing I'm just seeing a blank screen being shared.
A blank screen, okay. Let's see what we can do about that. what I'll do is I'll just close that one. Let's try that one. What can you see now?
Yep, that's it.
Okay, cool. Thank you. So over to you, Pete.
Okay.
Would you like to take us through your design and build of a 10-inch Dobsonian telescope?
Okay. Okay, so I'll start by saying thanks for inviting me to come and talk about the build of this telescope. It's been quite a while since I last did a talk, and it was probably about 2 years ago, and it was actually here in the Herschel Museum, where I talked about the actual making of the 10-inch mirror, which is normally sits in this telescope, which it isn't tonight, unfortunately, as Simon's just said, but yeah, so tonight is all about the actual build of the scope as opposed to the mirror. But just to give you a bit of background about myself, I've been interested in astronomy since I was a child, and then I started taking it seriously about 2004, where I started doing some planetary imaging with an 8-inch SCT. And then in 2010, I built a roll-off roof observatory in my back garden, and then started to sort of venture into sort of, well, planetary and deep sky imaging. I also do solar imaging as well. But yeah, I think my love of planetary imaging, I think, is what spurred me on to think about making my own telescope. I mean, the optic that's in the observatory is a 12-inch SCT. This one I built here is a 10-inch, but it is a precursor to a bigger one. So there's a 20-inch actually in progress at the moment. So yeah, bigger things to come. But this scope build and design was really like a precursor to finalize design, make sure it all worked, and yeah, essentially then to scale it up to bigger things. But you know, sort of aperture is king for high resolution planetary imaging. So yeah, hopefully by the time the planets are nice and high in the sky again, I'll have the 20-inch finished. That's the plan anyway. So is that sorry, is that working, Simon? The clicker? Oh, right.
Just give us a shout.
Okay. So yeah, so just an overview of the presentation. A few words on why build your own telescope. Selecting the materials. Design considerations, because there's numerous different designs for Dobsonian telescopes. A bit about the two-part design process itself, then the actual building of all the parts, and then testing and first light observation and a bit of imaging as well. And feel free to ask questions as we go along. I prefer that actually, rather than sort of, you know, wait until the end. If anyone wants to ask a question, you know, about one of the slides or anything, then just feel free to, you know, to go for it.
Can I now, in that case? If your interest is imaging, why Dobsonian?
Because they are great for planetary imaging. Not so much obviously for deep sky, where you're doing long exposures, but for certainly, I mean, I've started using this one for imaging the moon, and you know, it's perfectly doable, and you can actually fit, you know, tracking onto them if you so wish.
Yeah.
I went another route, which I'll talk about as well.
Because you know, Dobsonian, you know, I have one basic because I'm a visual observer, and it's a way of getting maximum aperture at a minimum cost, basically.
Yeah.
Yeah. But it's not usually the reason for using it for just imaging. But,
so why build your own telescope? Oops, it's working now. Oh, sorry. That one. Is this working, or was it? It was working, I think. So why build your own telescope? Control of quality. So you are in charge of quality assurance. So it's really, you know, I mean, how long do you want to spend on it? You know, you can keep going, keep trying to perfect things, modifying the design as you go. It's really up to you. I mean, you know, you can set your own goals and see what's possible, you know, sort of challenge yourself to produce something better than you can buy off the shelf from one of the, you know, from one of the well-known manufacturers. Also knowledge, just to improve understanding of the optics and the mechanics behind astronomical instruments. I mean, you know, I've used telescopes for a number of years, but you know, actually going about designing and building one was really sort of starting from scratch. So yeah, I mean, going through that process does improve your understanding of how these instruments actually work, and also the personal satisfaction of being able to sort of see the universe from, you know, something crafted with your own hands. That's particularly satisfying. And I did luckily get to see Saturn as one of my, well, I think it was the first thing I looked at through this telescope, which was very, very satisfying. So yeah, that's makes all the hard work worthwhile. So the materials choices, again, you've got sort of various options. Birch plywood is, you know, you can see that a lot of the components on this telescope are made from plywood. Birch plywood particularly is a good quality. It's very stable, doesn't have hardly any voids in it. It's often used for furniture making, and also, you know, it looks really nice in my opinion as well. But obviously, being, you know, a timber product, you've got to think about moisture. So, you know, you need to seal, all the parts were sealed to protect and against moisture ingress. Carbon fiber was another thing that I was thinking about. Obviously, coming from a Formula One background, you know, it's carbon fiber is what they build the race cars from. So I've got a fair bit of experience using those materials, but you know, they're very strong, they're very lightweight, and they're very, very small amounts of expansion, which is good. But obviously they are expensive and not that easy to process at home. So the majority, you know, of the, like I say, the build was ply construction. And aluminium, easy to machine. It's good for small parts, reasonably lightweight, and it does need surface protection against corrosion. I mean, aluminium does corrode. It doesn't rust, but you know, it does corrode if you don't protect it. But yeah, you can see most of the painted parts on there are aluminium parts. Okay. So the design choice. So this was, yeah, something I sort of pondered over for quite some time, actually. Just looking at, you know, what scopes using, you know, on the internet, just browsing what various designs are around, what people have done. You know, I saw a design that looks quite similar to what I ended up with here, which I like the look of. It employs a very low C of G, which helps facilitate large altitude bearings. So these parts here, because you can see on this scope here how big the scope is, but how large the bearings are. They're very, very small. The larger the bearing, the more it helps with stable operation and balance, which this particular design gives you. So, like, you know, when you feel visual observing and you swap out for, you know, a big heavy eyepiece, you can take a small eyepiece out, put a big eyepiece in, and the scope isn't going to, you know, wander. It's very, very stable. And like I say, the design is, I believe, you know, it's aesthetically pleasing and gets away from that sort of traditional boxy appearance. So yeah, I mean, these, you know, these sort of designs, they're very functional and quite easy to build and work perfectly well. But just from a, like I say, aesthetically point of view, I'm not that keen on those sort of designs.
So to finish the point, can we go back to the balance issue, because it is a real issue with the dobsonian.
Yeah.
So where is the COG in that thing?
It's low down. It's about 300 mil up from the floor.
So if you use something called a heavier eyepiece on that, when it's saying, you know, applying a full height angle, it'll then tend to, to move down, won't it?
Well, that's a problem with a lot of dobs.
Yeah, all dots. So how have you prevented that by having the level?
Just like I say, just purely by the size of those bearings. So these bearings allow the scope, the friction on the actual, because there's PTFE pads under those bearings,
Okay.
and the actual, I've got some pictures of it later, but there's in this area here,
Yeah.
you've got like a formica strip runs all the way around the bearing, and that gives you a certain amount of stiction, they call it. And based on the diameter of the bearings, it really holds a telescope, gives it good stability.
Okay, and that's enough to hold.
Yeah, you can. I mean, I can swap that out for a small eyepiece, put a camera in there,
Okay.
and it's just
So
solid.
Even near the horizontal.
Yeah. Sorry, are you doing it or me? So yeah, so the design of the components. So yeah, I thought about this for a while, and I saw a few people have used 3D modeling. I elected to go down the 2D route. I'm a bit old-fashioned, I think. I just like to work from drawings. So I found this software developed by Siemens called Solid Edge, and it's got 3D capability as well, but this was the 2D drafting version, and it's free. So I thought, great, let's give it a try. I mean, I tried a few others actually, but this one definitely sort of seemed to do what I wanted, and it was quite well laid out and sort of quite easy to get your head around. So I've got 2 or 3 slides. I'm not going to go into these in much detail, but it just sort of shows you the sort of design that I was doing in that piece of software. This particular shot here was just a screenshot showing you. It was basically calculating where the focal point was going to be, the focal plane here. So using all the correct dimensions of the design and the calculated focal length of the mirror, I was able to sort of do ray traces to be able to sort of work out where the focal plane was. And that's obviously a critical thing to consider when you're designing the telescope. You need to make sure that when you put your eyepiece in, it's going to come to focus. Again, this is just another quick screenshot. It just shows the slow motion controls. So this is this part here, and I was just sort of using sort of block fill, helps identify all the parts easily. So when you're designing and drawing these things, it's easy to get lost in all the dimensional lines and everything, but being able to sort of use all these colors to block fill makes things a lot simpler. Again, this is just a bit more of a close-up view of the design for the secondary mirror. So it's sort of standard sort of 2D engineering drawing stuff, really. But it's a nice, I think it has to be said, and if you're embarking on doing something like building a telescope, then it pays to spend a long time thinking about the design and actually preparing the design before actually going out and trying to make the actual parts.
Was this your first telescope you built?
This is the first one I built, yeah. Like I say, I've owned a few telescopes, but yeah, this I've never embarked. I've actually built the mirror first and then built this after. But yeah, the design process, like I say, it's all done in 2D. It's a great little piece of software, and I mean, if I wanted to do a mod, I could come in, I can modify it if necessary, print off the drawing, take it into the workshop, and away you go. calculating. So yeah, you were talking about a centre of gravity. So yeah, this, like I say, this design lends to a low centre of gravity. But in order to be able to design the scope, you need to accurately work out how heavy all the component parts are going to be. And then from that, you can calculate the actual centre of gravity. So I have a target centre of gravity, which was basically the centre of that circle. If you made those main bearings circular, that was the target C of G. And basically by calculating or weighing all the parts, you can accurately calculate an actual C of G. So yeah, that's basically it's done by using moments. So you have a reference point, which is I took as the back edge of the bearing here. It doesn't really matter where that reference datum is, as long as you measure all the parts from the same point. So basically the secondary mirror housing, you calculate, you work out the C of G of this component, which is quite easy to do because you can literally just balance out to get it pretty close. And then you take a measurement from the design back to the reference datum, and you do the same with the primary mirror housing. And I did the same with the truss poles. And then you've got three dimensions. You got the 3 dimensions and the 3 component weights. And basically, when you've got the distance from the datum and the component weight, you can work out the moment, the weight distance moment. And then once you've done that for all the parts, you add them all up and you divide it by the total weight, and it gives you the C of G. So
You have to ballast the
yes,
mirror amount.
Yeah. Yeah.
So it's actually much heavier.
So that's one of the main.
The price you pay,
Yeah,
much heavier.
you do pay a price for a low centre of gravity, but yeah, yeah. So obviously, for every little small bit of weight you add to here, you add quite a lot here, because obviously the balance point being so low, obviously. But then if you move that further up, then you sort of compromise in the size of this bearing. So it's a bit of a compromise. Depends what you want, to use the scope for. I mean, if it was purely visual, then scopes with higher centre, C of G's is perfectly fine. But I had in mind I wanted to sort of get something a real stable system.
Buying ballast. So I've had dogs where I had to buy ballast.
Yeah.
Buy a get a bigger 2-inch eyepiece. I mean, buying 1 kilogram ballast.
Yeah. Yeah. I mean, there's ballast in there. I've got some slides. I mean, I've built that myself as well. I thought it was just easier. So, but yeah, I mean, is that fairly clear on why that was done?
What's the F ratio?
F5.
5.
So yeah, I mean, one of the most important parts of the whole scope build was designing the mirror cell. Obviously, I designed the mirror, ground the mirror, which took a lot of work. So when you've ground a mirror to the standard that you were hoping to achieve, the last thing you want to do is put it on the mounting in the scope, and then the mirror slightly distorts out of figure. So obviously, so the considerations of the mirror cell was obviously a key thing to take into consideration. And I used a piece of software, which again is a free piece of software. It's called the Plate Optimizer. They call it PLOP for short, but Plate Optimizer. And this allows you to put in the parameters of your mirror. So this is just a screenshot of the input. So you've got things like the diameter of the mirror, the thickness, the focal length, diameter of the secondary mirror, any central hole, which obviously there isn't on this one. And then you've got how many points you want for your mirror cell design. So these points are the actual points which actually support the back of the mirror. So the points at where the mirror touches the actual support, the mirror cell itself. So I went for an 18-point design, which is probably overkill for a 10-inch mirror. You tend to go, you know, you up in the amount of points, the bigger you go. So obviously, the bigger the mirror, the heavier the mirror, the more support it needs. But you could probably got away with 9 points quite easily. But I thought, why not? I'm going to be building a 20-inch, which is going to be an 18 point. So get the practice in now. So yeah, so this is an 18 point. So you can see here, this is the output from putting in all your parameters. You get an output, which gives you your mirror cell, and then you get your connecting rods and the various dimensions, the lengths, and you get the triangular supports again with the dimensions.
How do they attach to the mirror? How do they attach those points? How do they
the mirror literally just sits on them.
just sits on them?
So this type of cell, it's what they call a floating mirror cell. It's literally it's just when you put the back of the mirror on it, it just sort of conforms. There's no resistance. That's the idea. The mirror just sits there naturally, in its as much of a free state as possible.
And when you're moving the telescope around, it doesn't tend to budge.
There's always that risk, obviously, with the bigger the mirrors. I mean, you know, you see people put slings around them and all sorts. So when they're using them very low down, and they're supported. So there is probably maybe some additional design considerations I've got to do for the 20-inch, because yeah, I mean, albeit it's only twice the diameter of that mirror, it probably weighs about 10 times as much, I would think. Yeah, I mean, for this, it's just supported on 3 points around the edge, and so far so good. But so those design outputs from that plate optimizer, then you can take, and I use the dimensions to design those parts in solid edge. So those are the support triangles, and that's the actual assembly with the aluminium. So yeah, so and there's the distance. I mean, you got these distances are obviously quite critical, because it's basically plate optimizer. What uses what they call finite element analysis to calculate all those points. And then this was the actual design of the actual mirror cell assembly. So this is the actual the 18-point mirror cell, the actual backing plate, and the mirror surround itself, which you can see here. Another thing I took some time over was coming up with, I mean, I probably get this from my day job at Airbus, but we see a lot of these on our drawings. They call them bombs or bill of materials. So from the design, it's just a big list of everything you're going to need to build the scope, whether it's all the parts you're going to manufacture or bits you're going to buy in. Obviously, I didn't make the fasteners. The bolts, I obviously bought all this. They're all stainless steel, but stainless steel bolts, and basically every part that you're going to require. And I broke it down into the various components, so you can see here where it's used. So you got the upper tube assembly, turntable, and then this is just a section from here, but just all the major subcomponents broken down into all their constituent parts, how many you're going to need, whether I'm going to buy them, whether I'm going to make them, that sort of thing. So again, it's just, yeah, making sure, I suppose I just picked this up from obviously years of doing this as a day job, really, but yeah, it was good to do it this way. Certainly helps when you actually come to you know, make the actual telescope itself. So now I've got onto the actual build. So what I've done is I've just put slides together showing the major components from sort of the bottom up and how I went about making them. So the turntable, as you can see, is majority of it is the birch plywood. It's 18mm thick birch plywood. and this is obviously the 2D design, and then these parts here, the baseboards. So yeah, the birch ply itself comes in an 8x4 sheet. So it's basically having to cut all these parts out initially by using a router. So I cut them out by router, or I've got a little small bandsaw as well in the workshop, and a disc sander. And pretty much between those sort of, yeah, the router, the disc sander, and the bandsaw is pretty much what I use to, you know, tool wise, to make all the plywood components. So inside the turntable, so there's two boards, and in between the two baseboards, you've got a bearing, which I actually call a lazy Susan. I don't know why they call it that, but that's what they call it. A turntable bearing. So that screws to the baseboard, and then the top board sits on these little white plastic features here, and then one ring rotates around the other. And then in the center, I've got a friction pad. I don't know, I hadn't seen any other telescope use that, whether or not they do or not, but quite a lot of people tend to use the Formica and the PTFE to give it stiction, because without that sort of friction pad, the bearing on its own, you know, it's completely free running. So you would never control the telescope. It would just, you know, it would just blow around in the wind, if you like. So that is literally just a piece of carpet tile stuck onto a smaller board, and then the central bolt, which goes through the middle, through there and out the bottom with the nut on the back, you can use as a tensioner. So if you tighten the, you know, you can tension up a bit more, and it will give you just, you know, that bit of friction. So you can still move the scope nicely, but it will, once you let go, it's not going to sort of drift away. Obviously that's, you know, like I say, if it is windy, you don't, you know, you want to make sure whatever you're looking at is going to stay in the eyepiece as much as it can. And this is just another view of the, so the turntable. Here you can, like I say, I've got it pointing to the so the central pivot tensioner bolt. These are the PTFE bearing pads. So there's 4 of these. So this is the 2D design of the actual rocker. So this is the actual rocker, and on the rocker you've got these PTFE pads, which are about 6 mil thick, and there's one there and there's one there, and same on the other side, and then a Formica strip which runs all the way around the bearing in a recess. So you can see this recess here, which takes the actual form. It's not actually Formica. It's a very similar product, but it's very similar to what you'd have on your kitchen worktop. Basically, it's not dead smooth. It's slightly rough, and that's what gives it the stiction to these pads. Again, so you know, you can move it in altitude, and when you let go, you know, it has that little bit of stiction. So you've got to give it a little bit of a push to move it.
The PTFE wear out? Do you have to replace them every now and then?
Yeah, I mean, you do see a little bit of residue from those, but I can't imagine it's going to be quick. It's going to take some, you know, because obviously PTFE is a nice slippery substance. But yeah, I mean, it's not a major issue. I mean, they're literally just 2 little self-tapping screws, which you can see there, which hold them on. And I just cut them out of a little bit, you know, you can buy it in sheet form and then just cut it out to size. And yeah, the rockers themselves mount into the baseboard in a rebate. So I don't know if you can just see there's a rebate in the baseboard, and then they're bolted down into threaded inserts in the base. But the rebate gives it a nice solid lock, you know, feel. I mean, all on bolts, there's nothing, it's not glued in or anything. It's literally just held on by those M8 button head fasteners. But
Can I go back to the friction point? I mean, how did you calculate or decide how much friction you want to have in there?
it's a bit of trial and error, to be honest with you. Yes,
And if you want to increase it or decrease it, how do you do that?
you can make them larger, just make those pads longer, so you've got more surface area. That was just a gut feel initially. You know, I mean, you can, like say, looking at what other scopes have used, it was just, yeah, that looks about right, we'll give that a go.
But if it's not enough, or it's too much, you can just redo it.
Yeah,
do it differently.
yeah. Yeah, so that's, yeah, that's pretty much essentially the turntable. There's 3 pads on the bottom as well, which unfortunately I didn't have a photograph of, but you can just about see them on the photo, just poking out there. But there's 3 circular pads, trying in a triangle formation with a rubber base on them as well. So it's you know, it's nice and grippy. But yeah, that's essentially the turntable.
So it's designed to be used on a very flat surface, not on sort of grass and road.
I mean, I've had it out in the lawn in our back garden, which is reasonably flat. I thought, I mean, it's obviously it's more stable if you have it on a solid ground. I mean, I thought about, you know, you could literally have another board, if you like, with a couple of some spikes in it, which you just press into the soft ground and then sit that on top. But yeah, but yeah, there's but yeah, just going back to the mirror cell again. Here you can see the actual cell itself. Got the collimation points. Did I not miss a slide there? Did I? No, that's right. That's right. Okay. So these are the collimation points. I've got a picture in a minute of those, design of those. These are the mirror posts. They're made in aluminium. There's 3 of those, again in triangular formation, to give an equal support to the edge of the mirror. And then these are M5 nylon fasteners. This one here, the bottom ones, they support the edge of the glass, and then the top one just screws in, literally just glazes over the top edge of the mirror without actually touching it. It's about 0.5 mil gap, I suppose, and you just wind those in so the mirror can't fall out. You know, if you're using it at a very low altitude, it can't accidentally roll out. And then you can see the edge of the some of the triangle supports here. And these are actually the primary mirror lock. I decided to go with this. I mean, as it turned out, I don't really think they do that much. I mean, the actual collimation springs were quite powerful springs, so it's actually it holds collimation really well on its own. It's a push-pull type collimation system. But yeah, when I design or when I go to do the larger scope, I'm not sure if I'll put those in, but they're there anyway. But yeah, the idea is, you know, once you've collimated the scope, you just wind those primary locking screws in, and it just holds everything fixed. It can't sort of move at all. So yeah, so this is just a close-up of the 2D design of the collimation system. So this is the back face of the telescope, and this is the inner, what I call the inner cell ring, and then the mirror would be sat here. It's basically 3 stainless steel M8 fasteners, which run through a spherical bearing at the top, and then through a 30 mil long stainless steel spring, and got a couple of stainless steel washers either side, which the spring actually sits in between, and then it runs out the back. Again, I've got another washer here, and then a PTFE washer and a knurled stainless steel like thumb nut, so you can adjust it quite easily by hand, or about sort of an inch, just over an inch diameter. So in the PTFE allows a nice smooth So the PTFE washer allows a nice smooth operation of this nut. Obviously, if you wind it in, it compresses the spring and pulls that side down. Obviously, as it comes down, that there's a sort of, obviously there's a bit of an angular movement going on in here, which is why you need the bearing. So there's 3 points like that, and then obviously this is what's saying the this lock screw here, which is just basically a threaded insert, and then a stainless steel washer here, and you just wind that in, and it basically just it just locks everything in position. But like I say, in use, I don't think I haven't really been using them that much. The springs seem to do the job well enough on their own. Okay, so here's a better view of the mirror cell. So here you can see what parts are made out of what. You've got, like I say, these support triangles, 6 of those, and then it's actually mounted. These are mounted on spherical rod end bearings. So like what you would find on the end of a car, track rod end that turns your wheels on your car. So there's basically a rod end bearing here. There's another one here, and there's one there. So you've got like a free floating system for these actual mounts, so it can rotate in that axis and that axis. So basically those triangles have got free movement. So the whole cell then is just like a floating cell, which when you put the mirror on, it just conforms to the back of the mirror without putting any sort of undue stress on the glass. And then this keeper ring is basically on these parts here. They just hold everything in place to stop it rotating. So the whole system then is as per the output from the plot design. So the mirror supports then are in the correct orientation. And these again are nylon, just nylon nuts, and that's they're slightly concave, which is good. So the actual mirror sits just on the edge, on all these points. I just skim them off in the milling machine to make sure they're exactly the same thickness. These are the collimation bolts I was just talking about. They're actually milled flat on one edge, and then this little block here is just screwed against that flat to stop those bolts rotating. So when you adjust the collimation screw from underneath, there's no chance of those spinning. So it's basically an anti-rotation system. And that's a better view of the actual underside. So these are the rod end bearings, and there's one here. So you've got 3 of these like T sections which hold the 6 mirror triangle supports. And you can see the nylon fasteners. But positioning these is obviously critical. So getting this exactly in the right place, in the center. Also the lengths of these. So the distance between the center of that bolt and the center of that bolt is spot on. In order to do that, I just had to mill the ends of these slightly, and I made a little jig. So I made a little jig on my milling machine with 2 holes in it, exactly the right distance apart, and then I could drop the jig onto those bolts just to make sure they were spaced exactly right on all 3 points. But and again, that's with the actual mirror in position. So you can see those retaining bolts. They just come over. Well, you can obviously wind them in as much as you like, but they only need to come over a couple of mil. It's not going to go anywhere. Then it's nice and safe. And again, this is just another picture showing the actual supports. You can just see them touching the back of the mirror, and then you've got that's the lower bolt, which just basically winds in and supports the mirror so it can't move around. that, you know, laterally inside the actual primary mirror housing. And then another, I mean, really, this is sort of the finished assembly. So it's basically I've painted all the aluminium parts with a very, very flat matte black. All the parts really, well, the majority of the parts are painted in the mirror cell area. You want to try and avoid any sort of unnecessary light reflections going on in there. It also improves your contrast as well. Okay. So the main bearings. So yeah, these were plywood construction. Again, 18 mil thick plywood, cut out with a router. And what I do, what you can see in the bottom picture here is the four pieces. So each is made up of two 18 mil sections. They're basically they're slightly different inner diameters because of the step there for the, you know, for the Formica strip. But I've bolted them all together there, so they're all in a stack to enable the surface finishing of the outer of the inner surfaces. So you can surface finish them all at the same time, so you get them exactly the same time, exactly the same size. Finishing the inner surface was quite, you know, quite time consuming because I had to do most of that by hand. But on the outer surfaces, it was much easier. I could do them on my disc sander. Yeah, so that's really all there was to the main bearings. I mean, you've got these mounting points as well, which I've got a better picture of, I think, on the next slide. So yeah, so mounting the actual bearings to the secondary, the primary mirror housing was done with three M8 cap head fasteners on each one. So there's two on the inside. So this is a picture of the inside. So you've got these two here, and there's one on the outside, which you can see there. And they thread into threaded inserts in these inserts here, which is in this back board. So it's actually, those inserts are actually what they call T-nuts. So the actual inserts are installed before this assembly goes together. So they're actually contained then. So you can put quite a lot of force on them. They're not going to pull out because of this T. They're actually, you know, you can't pull them through, which you possibly could with, if it's just a threaded insert. If you put too much torque on those fasteners, it could quite easily pull out. But those T-nuts, that's the design. And this little bolt head support as well. The reason I did that is because to mill these slots out, was a lot easier to do them this shape rather than trying to make them with a square end. So I just manufactured some little aluminium supports which just pop in with a hole in, and then they just push the bolt in, and then obviously just gives a flat surface for the bolt to torque down onto. And there you can see actually what I was just talking about, the T-nuts. So they're actually mounted onto these frames. So that's the lower frame. And then this was the building, the primary mirror housing. So this is just a bit of planning to try and work out how to cut all the pieces out and save us, you know, there's minimizing the waste, or you know, doing it as efficiently as I could. So yeah, so that had to be all cut out by a router. You can see all the points. These points here is how I fixed my router. So I actually had the router fixed onto a fixed point arm, so I could actually cut them out with the router into the circles. And then so once all those parts were cut, it was a case of then stacking them up, gluing them all together. So those parts are all glued together, and then surface finishing. So finishing the inside again was mainly done by hand using I just used a big offcut stacked up several offcuts of ply. It's got aluminium oxide on the inside, and just literally sanded that by hand to get that nice and smooth. And then the outside was done on this sander. And what I've done here is there's a board here you can see clamped to the disc sander, and there's a baseboard there which isn't actually part of the housing itself. You can see there's 1, 2, 3, 4, 5 layers. This baseboard is just temporary fixed, and then I've put a central point through that board into that board, which is clamped. So that means I can rotate that round on the disc sander just to sand and get it perfectly circular. So we get a nice smooth finish, because if you try to do that just by hand, it'd probably come out like a 50p piece. So yeah, that was how I got all these sort of surfaces nice and smooth, and there's a bit of hand finishing as well. But yeah, that saves a lot of time doing it like that. And then you can see the actual finished primary mirror housing here. These are embedded T-nuts. This is for mounting these truss mounts. So that's the truss mount, and then it's flocked inside as well. So just again to prevent any internal reflections and improve the contrast at the eyepiece. And we're talking about earlier about make it ballast. So yeah, so behind the mirror, obviously with this calculation using what we talked about earlier, calculating the C of G and all the weights of the major constituent assemblies, I pretty much had a good idea how much ballast I needed to make to go into the primary mirror housing. And so all this was just basically offcuts to make a mold. So that's, you can see this is all the mold, and then I released all the surfaces with like a beeswax and used lead shot and epoxy resin. So that's just lead shot all poured in dry initially and leveled, and then pour in epoxy resin, let it set, take take it out of the mold, clean it up, sand it and paint it. And then I think there's yeah.
So what's the mass of the balance?
Good question. I can't remember now. It's probably about 2 kilos.
Just 2 kilos.
A couple of kilos. There's actually, but yeah, you can see the primary cooling fan as well. That's just to help cooling the mirror down quickly when you take it out from indoors. And these are the holes are just to help that air circulation around the mirror.
What have you got powering the fan?
It's just a little I don't think there is a picture of that later, but it's just a little you can buy these sticks for charging your mobile phones.
Oh yeah.
And it's just like a little stick battery for light. It just velcros on the back to run the fan. But yeah, I think there was a picture of that a bit later, but then again you can see the collimation points here. So metallic parts. So I knew if I wanted to make everything, or as pretty much as much as I could, then I was going to need something to machine metallic components. So I ended up buying this little 3-axis milling machine, which stands about so high, I suppose, but it weighs quite a bit. So I had to use a chain block to actually lift it off the floor to get it on the bench. But yeah, I mean it's a great little machine. It's got what's not pictured on here. It's got a 3-axis digital readout as well. So you've got actually magnetic scales on all 3 axes. So when you move the drilling head or the slide table, it actually outputs a digital readout. So, you know, it makes life so much easier when you're machining parts. But here you can see this was the actual secondary mirror holder, starting work on that from basically a solid piece of aluminium bar. That's what they call a rotary table, which does exactly what it says really. You've got a lever and you can turn it and it turns around. So in order to mill those grooves for the spider veins, I can actually use the rotary table to rotate this. It gives you another axis basically for machining. And this is the actual secondary mirror holder. I was just about to start cutting or skimming the angle for the secondary mirror. You can have a look at it. It's in there. But yeah, so that was. I mean, I took all these photos not just for this presentation, but just to remind me what I did. Because one of the most important things. Often you think, how did I do that? I can't remember. So take lots and lots of pictures. You know, when I come to build the other one as well, I can always refer back. So yeah, so I showed you that picture a bit earlier, but that was the 2D drafting of the actual secondary mirror holder, and that's pretty much the finished article before I painted it. One thing I did modify, I put these lightning holes. I wasn't happy it was light enough, so I actually took those and milled out completely all the way around, so it's completely hollow. And again, similar with this part as well, to try and get it as light as possible. Because like I was saying earlier, you know, the more weight you have this high up, you need a lot more weight down here to counteract it because of the low center of gravity. So getting as much weight out was something I didn't actually think I would have to go that far, but it was necessary in the end. And these are the again for the collimating the secondary mirror. And some little PTFE adjusters, because you've got to be able to rotate that this way in 360 when you're setting up the secondary. You need to be able to rotate that way and also adjust the angle of it. So you need all those abilities to be able to line the mirror up with the primary. So and these were just some fasteners where the spider veins holds the spider veins on.
I was puzzled that you had to do that to lighten the secondary holder a bit, which wouldn't take much out, and yet you say it's robust enough to have quite different weights of eyepiece, which might vary by half a kilo.
Yeah. Well, you can have after have just have an adjustment. It's all down, like I say, it's all down to those bearings. I mean, trying to get it. Obviously, there's learning to take from this when I build the bigger one. I probably will try to go even lighter on the actual secondary mirror housing. But I tried to get it as light as I could in order to cut down on the amount of ballast that was needed.
So there must be limits. There must be some massive eyepiece or camera.
Oh yeah, if I put my deep sky camera on there, it probably wouldn't take that. But for what I'm using this for, certainly swapping eyepieces, putting Barlow lenses in, small little planetary cameras, it's fine. Yeah. Here's this. These are the spider veins. They were just made from flat aluminium sheet, about 1 millimeter thick. I think it was folded at one end, and then they're screwed on onto the actual secondary assembly. And then there's actually, I haven't got a picture of them here, but there's these are actually threaded bolts with a slot cut in. There's 2 of them on each of these spider veins, which they bolt on here, and you can see coming out here. So those little nuts go on the end of these threads, and that holds the whole assembly inside the actual housing. And also you've got the adjustment there as well to make sure you slacken one side, tighten the other. You can adjust it so you make sure you get everything dead centralized. and this is the actual picture of it actually installed. So again, all painted. These little knobs here, I 3D printed those just to help me adjust, get away from having to use an Allen key, which you don't really want to do in case you drop it down on the primary. So yeah, so those are just 3D printed, and those are as well actually. Those parts are 3D printed. They're more than strong enough for what they actually do. Again, these truss clamps. So these were just made from flat aluminium stock to this design, all on that little milling machine. So you've got the 8 blocks all together. And what holds the actual truss into the block is a spherical end. So this is a spherical, like a rod end again. And then this is what I call an end stop. So that the rod end threads into that end stop, and that end stop actually gets bolted into the end of the truss pole.
Is it like a bearing then?
Well, if you this is a clamp. So this bolt just clamps. So it's a spherical bearing, and it's just a round hole basically. It just slides in. You tighten that up, and it grips it.
So it just sits against the bearing.
Yeah, it just holds it by friction. And you'd be surprised. You don't have to tighten them up that much. It really does hold it well. But yeah, that's and then like I say, these bits just slot into the end of the truss poles. But yeah, I mean these these were done on that rotary table I was just mentioning, because I don't actually have a lathe, so any parts that are round I actually did on the vertical mill using the rotary table. Probably it would have been quicker on a lathe, but yeah, I managed it in the end. But yeah, it worked. So I did it the hard way. And this is just a picture of me starting to paint some of those parts. So yeah, so everything, all down to the prep again when you're painting stuff. Thoroughly degrease everything. We use an etching primer, leave for 24 hours just to etch. Yeah, so this is that really flat matte black, which was I used as a top coat. Here you can see the spider veins, these truss blocks, the end caps. So all these parts you can see which are black. I just sprayed them all myself, and it's quite tough. It took me a little while to find the right matte black. It was the flattest one I could find, basically. It was, I think they use it for like, I think it's like a military grade aerosol black flat matte paint, but yeah, it's pretty tough. I was thinking about anodizing, but yeah, I thought I'd try and save a bit of money, because getting things anodized isn't that cheap. So yeah, so far so good. And those are all the poles, all cut to length.
Did you just buy standard tubing for that?
That was just stock tube, cut to length, and then again primed and painted. Yeah, and this is one consideration, is that even though you've done all that design work and you think you know where the focal plane is going to come out of the eye, come out of the focus tube, I thought, well, if I cut on my aluminium tubes and there's something not quite right, and if I've made them too short, I can't extend them. If I made them too long, that's not too bad, you can cut a bit off.
Yeah.
But if you make them too short, even if it's just a few millimeters, you can't add them on. Sorry? Yeah. But this was, I thought, I've got some old broom handles sitting in the garage. So literally those are broom handles with those spherical rod ends. I cut them all using a jig to get them all the same length. I set the telescope up, went out with an eyepiece, put the mirror in, went out with an eyepiece, and just made sure I could get focus. And I adjusted these slightly just to make sure if you could go through all my range of eyepieces, put Barlow lenses on and everything, all the combinations to make sure everything would come to focus. Because, you know, if you don't do that, chances are you get a nice new shiny eyepiece, you put it in, you can't get it to focus. So that was the idea behind those, and then just took that length and obviously transferred that onto these again with I used a jig which was just a long block, a long plate with 2 blocks on the end set at the correct distance, and then set all these up and literally just passed them in between these blocks just to make sure they're all exactly the same length, because obviously you get one slightly longer than the other, it's going to do all sorts of funny things. So yeah, easily get it within 1/4 mil, you know, with a setting jig. But yeah, that's all the poles. This was some of the little parts I machined up for these stabilizing arms. So it's just 2 brackets bolted onto the primary housing and the top of the bearing, because you could take those off, it'd be fine like that, but if you put the telescope right down, obviously there's a fair bit of weight there, and you can get it, you know, it can start to, so it was just a bit of extra support, and it made a huge difference when I added those. It really does, you know, those are solid aluminium bars, and yeah, stiffened everything up no end. So yeah, going, you know, observing right down near the horizon, the whole thing's still nice and rigid.
When you added things like that in, did that sort of affect your centre of gravity calculations if you had to kind of compensate for that?
It was minimal.
Right.
Minimal. It wasn't in my original design. It was something I knew I was going to need after I put the whole thing together, basically.
Right.
So it was a modification, but it was a good modification. I actually think it looks all right as well.
Yeah.
But yeah, I didn't go back and plug all those numbers in because it's pretty light.
Yeah.
And to be honest with you, I just put them on, then went out and tried it out. And like I say, there's enough stiction in those bearings to overcome any little issues like that anyway. That's just another view. So yeah, onto the secondary mirror housing. So again, all plywood construction, 18mm ply. There's the 2D design. Like I was saying earlier, these are like ray tracers. So this was the virtual focal point based on the focal length. With a mirror at 45 degrees, you get a like for like angular reflection. So you can calculate where those rays cross. So yeah, it wasn't bang on. I think it was within 10mm. So it was pretty, you know, it could have been a lot worse. Yeah, so I just, like I said, a small adjustment on those wooden poles just to get it just about right. But yeah, these, so you can see the 2 rings, top and bottom, and then you've got these vertical struts to hold the 2 rings at the right distance apart. Again, all stainless steel hardware, stop anything corroding. Again, some lightning I did on these struts, so these ones and this one. I actually ended up milling out all of this. So initially I just put these holes in down to a specific depth, but I wanted to get it even lighter, so I just milled it out completely to get it as light as I could. And then this was just putting in the actual the inner skin, which was 1/8 thick birch ply, so just over 3mm thick birch plywood, which in hindsight I probably should have gone a little bit thinner. Certainly for the next scope I'll do it at a 2mm, because it was probably a little bit overkill, because it literally is there just to sort of block any stray light.
You wouldn't think of using aluminium sheet aluminium for it?
It was, you could. I did it purely for aesthetics,
Right.
just so it's, you know, that was the only reason. Yeah, I mean, there's no reason why you couldn't use an aluminium in there, but yeah, but this is just setting it all up, gluing it in position. You know, all these little bolts I put in to make sure it was fixed. You know, lots and lots of points to get it to pull round. Hence why next time I'm going to use a thinner, slightly thinner. It was a little bit thick, but it did work out okay in the end. And then this was just finishing it off. So obviously once the glue had gone off, you take all the bolts out, filled all those holes. Here you can see threaded inserts again for the truss clamps. Yeah, just sort of, you know, getting into finishing stages here. And then an anti-reflection flocking on the inside. That's pretty much there. And then focus and mounting. So I went for a low profile Moonlight, dual speed Crayford. Nice focuser, nice and smooth. And this was, again, the 2D design just to enable me to position that correctly in relation to the secondary mirror. You could do it. No, you could do it. You could do it. I mean, I thought, you know, I thought it would maybe look, if I did do it, it'd probably look a bit more agricultural, maybe. But I think it's possible. I mean, but you know, I think I went, you know, I did sort of bottle out a little bit and went the easy route. But yeah, no, the good.
Really.
No, I know, but yeah, no, the nice focusers, the Moonlights, they are nice. So yeah. And this was installing the actual secondary mirror. So this was the actual part I was showing you earlier. The aluminium part there ended up milling out completely. So it's completely hollow, apart from a central like post. So the central post. And then this is a little piece of carbon fiber, which I use for the backing plate. So obviously a secondary mirror is ground perfectly flat. It's very, very, very flat. And the last thing you want to do is put it on something which is going to thermally distort or move or anything. So that was the only time I used a bit of carbon. Had a little bit of spare in the garage actually, so just came in handy. And yeah, that's what I use that for, because it's very low expansion, very, very stable, nice and flat. This here was something I'd actually seen other people do, and I thought that's not a bad idea. It's a safety tether, because your secondary mirror is stuck on there with little blobs of silicon, and you know, in the unlikely but not impossible event of your nice, you know, shiny secondary deciding to part company, you know, if you're looking up at something at the zenith, you know, drop straight onto your primary. So yeah, this was a safety tether, which was just a piece of, basically it's just a piece of fishing line. I've got another picture of it as well, but it's basically glued onto the back of the secondary with a bit of epoxy, and then there's a little bolt in there which holds the other end. It's just tied onto a bolt, so if it does decide to part ways, all being well, it should just hang there. And this was the 2D design for the location of the secondary mirror. And one thing is that the actual optical center of a secondary doesn't actually sit on the actual center of the actual holder. There's an offset. So you have a geometric center and an optical center. As you can see, it sticks out further one side than the other. And you can see the ray trace coming in. And it's because of the angle. It's just purely because it's mounted at 45 degrees that side is sitting closer to the primary than this side. So the actual rays hit at the same point. The distance in from the edge is the same, but the actual mounting of it on here, you could be fooled and think, oh, I'll just stick it on right in the middle, you know, so it's sticking out the same either way. but then you wouldn't, you know, it wouldn't actually, you'd lose some of the light being reflected from it. It would actually shoot off the edge. So there is an offset you have to consider. And again, with a 2D drafting piece of drafting software, you can just calculate the offset quite easily. It was just 3.2 mil. So just, you know, I can mark the back of the mirror when I actually came to fix it on. And this is just the, again, these are the 3 blobs of silicon. Again, it's just 3 because it's a sort of triangular, you know, there's a plane, if you like, 3 points gives you a plane. It's aquarium grade silicon. So it's yeah, it's got good thermal properties. Yeah, you can see the actual, well, there's a better view of that tether I was telling you about. So there's just a blob of epoxy resin on the back, and then there's a little bolt there where this is tied around. Obviously I shortened that, so it's, you know, it ends up being quite short, because if it was a long tether like that, if it did decide to drop, it probably just popped the epoxy off. So yeah, but yeah, and there's the actual mirror in place. It's on some little shims, these little shims here, to make sure it sits at an even distance above that back plate.
So obviously you put the blobs, the circle in, and then you put the mirror in. How did you get that perfectly flat?
Yeah, that was it. Just using those 3 shims. And all that was aluminium foil tape, aluminium sticky tape stacked up to about 2 millimeters. Measured it with a vernier to make sure they're all the same. Just stuck them in there on a little bit of super glue just to hold them. Stuck the mirror on, and once the silicon had gone off, just tease those out. And this wasn't actually part of my original design, but I did start thinking about it as I was starting to build the scope. I thought, you know, the one thing, if I'm going to do any sort of imaging with it, is obviously I need to be able to sort of keep the objects in the field of view, to do even, you know, even lunar imaging. So yeah, I thought about doing you know, motor controls, but there was just something, I don't know what it was. I just thought, you know, I fancy just trying to do something a little bit, you know, not too fancy, just keep it relatively simple, but just using some hand controls. And this was the design I came up with. I'd seen other types of design using belts, like a belt running around, but I hadn't seen anything done exactly like this. So as far as I know, this was a unique feature, and I ended up using a 3D printer timing belt and gears. I went through various different things, think, what can I use, you know, to be able to give me good engagement, so, you know, it's nice and positive, you know, it's you know, when you're tracking using it, you want very fine adjustments. And I know I actually did trial a few different things, rubber, you know, almost like friction based materials, and it just wasn't going to work. And then I was just looking at my lad's printer, actually he's got a little 3D printer, and I looked at that and I thought, you know what, that might do it. So yeah, went onto the internet, lo and behold, just it's quite cheap, bought some of this timing belt. And that rubber belt, you know, it's nice. It's almost like, yeah, it's like a timer. It's got fibers within it, so it's very non-stretchy. It's it's rubber, but it's got obviously it's like a timing belt in your car. You know, it's very, you can't stretch it. So and then the gears, bought these gears, not those particular ones actually, but these ones you can see here, and it gives a really nice, good engagement. And the belt itself is just it's just bonded onto the it's just bonded on with a high strength contact adhesive. And then these gears, these little steel gears here, they're off an RC racing car, off the motor. So yeah, it's a smaller gear here, just to give me the right ratio, so I get good control. So about 10 to 1, I think, or 12 to 1. I can't remember the exact ratio now, but yeah, it gives you a nice sort of control of the actual azimuth and altitude.
Is that the belt we can see like round the top?
Yeah, so that's that grooved belt here, and there's one here as well running around the edge of the main bearing.
Right.
So there's another one of these wheels at the back, just under there. There you go. So it's just a bit of better view. Again, these are these steel gears of an RC racing car. You've got some little universal joints, 2 universal joints at the top for the actual hand adjustment. And there's bearings, there's some, all these little, the actual shafts themselves run through bearings in the actual plywood, just to give you a nice smooth operation. There's just a few different views there as well, so you can see the back one there, which you can't see so well there. And then there's the again the azimuth control on here. You can see a better view there of the Formica strip as well on the PTFE. And then one thing I thought, I was saying earlier about sealing everything. This actually showed it up quite well. So all that, I took everything apart, sealed everything individually with Osmo, which is, it's quite a well-known product, but it's really good. It goes on so nicely, gives you a lovely finish. It's not like painting varnish, varnish is like all sticky stuff, and to get a really nice finish with varnish, so I went with this Osmo oil, and you just wipe it on with a cloth. It's so easy, and it dries, and it gives UV protection, lasts for years. It's not, it's quite, yeah, it's really nice. You get all different finishes on it. It's yeah, it's really good stuff. And that was that's the finished article, which you can see here, obviously, but that's with the shroud in position. So obviously the shroud is important, just to block out any stray light. That's just made for Lycra, and my good wife did the sewing work on that to stitch it together. But yeah, and there's a little Celestron. I didn't make that bit either, but that's a little Celestron red dot finder, and I brought that because it's so light. It was the lightest one I could find. It's only about probably about 800 grams or something. But yeah, very light. And then a few more slides, I think that's nearly there. So yeah, just before first light, then, I mean, some things I had to consider. Getting through good thermal equilibrium, leave it outside for a while just to make sure the mirror's cool. Collimation, obviously it was way out initially when I put everything together, but yeah, collimate it. You have a little on the primary mirror, which isn't on this one. I've got a little sticker right smack bang on the center, like a little this little round sticker, and obviously because of the light doesn't actually hit the dead center of the mirror because it's blocked by the secondary. So you're not compromising any light by doing that. It just helps you align the secondary, and you can use a laser collimator, and you can fire the laser down. You use the adjustment knobs on the secondary just to get the laser sitting in the dead center of the primary, and then you can use the back collimation knobs to do the fine adjustment, just to make sure everything's collimated and nicely aligned. I thought, what should I use? I thought the moon would be a good first light target. So that's what I used. And then it's a case of, I was pretty nervous, I must admit, after all that work, the mirror, all that grinding work on the mirror. And I was thinking, oh, here we go, cross everything, have a look. And yeah, what a buzz. It all came to focus. And I thought, oh, it was just such a relief. And then, yeah, star testing. I've done some star testing. That just basically lets you know if you've got anything significantly wrong with your mirror. It's such a sensitive test. It will show you any minor imperfections on the mirror, such as any turned down edge, astigmatism. You know, those are the main things to look for. If you've got a defocused, you basically, you look at a star, a reasonably bright star with high magnification, you defocus it slightly, and you look at that image of a defocused star in the intra and extra focal positions. So you basically go inside of focus, you look at that image, you look at the outside of focus at the same distance, and then they should, if they're not on a perfect mirror, they look exactly the same. If they look exactly the same like that's in the picture, then you've got a perfect mirror, which is incredibly unlikely, if I'm honest, to get it absolutely perfect. There's always something, because it's such a sensitive test. But I mean, I think, I mean, with the seeing conditions, it's not always that easy. If you've got really nice steady skies, you get a nice diffraction pattern to be able to look at that. And from what I've seen so far, it doesn't look too bad, so I'm pretty happy.
That's a collimation test too, I suppose, isn't it?
Yeah. Yeah, you can do really fine-tuned collimation using defocus star like that. But yeah, for actually testing the primary mirror and the secondary and the whole setup, a star test is the most sensitive test you can do. It shows the slightest imperfections, but you need steady starts, steady skies. And then there you go. There's a couple of pictures.
That's incredible.
So
As long as we can't touch it.
So that was taken with this one, using my little planetary cam and the hand controllers to, that was about a minute exposure. Just to, so yeah, I'm sitting there with my hands and just watching the screen and just, you know, literally just controlling everything with a, by hand. But it's yeah, it's quite good fun actually, quite enjoyed it.
How many frames does that extract?
That was about a minute exposure, about sort of 80 frames a second, whatever that is. Quite a few. I took quite a lot from that night. And there's another one. I think there's one more. Yeah, there's another one there. But yeah, so yeah, onto the 20-inch.
Wow.
That's
So, thank you.
Thank you, Pete. So, how long did it take you to build? How much did it cost? And how long
Well, from start to finish, if you include the mirror, because I actually built a machine to grind the mirror as well. So I think it's taken about 2.5 years from starting to build the actual mirror grinding machine to the finished article here. It was about 2.5 years. Yeah.
Does that include the design time as well?
Yeah, everything. Just having the initial thought of let's give it a go,
Yeah.
to actually, you know, taking it out for first light. But I've loved every minute of it. Really enjoyed it. Doing the mirror was really satisfying. I said I did a talk on that here a couple of years ago on the mirror making. But hopefully, you know, the 20-inch. I mean, obviously it's a lot bigger, but you know, I won't have to build another mirror making machine, because that will do up to a 20-inch mirror. And obviously the things I did sort of learn from this, you know, I can take forward now and you know, incorporate it into the larger scope. So so far, I mean, I've built the mirror cell, but I haven't actually started grinding the mirror yet. So I'm doing it slightly different. I think I'm going to finish the mirror cell and the mirror surround, so I've actually got somewhere to put the mirror when I've actually finished grinding it, because that's the best place to put it, really, to keep it safe. Is you put it on there, put the cover on. I made a little cover to protect it, and yeah. But
what type of ratio do you for the
f4.5. That will give me just about I mean, I might have to stand on a stool at the zenith, but yeah, just about, you know, so for most objects, then you can still, you know, not have to stand on anything, you know, little step ladder or anything. I want to try and avoid that if possible.
When you build that way, then give the 10-inch away to really appreciative members of other societies.
I might have to. I don't think I'll have room. I'm running out of room. But yeah, yes. When I say this one lives in the lounge, I'm not sure about the 20-inch. I think Joe might have something to say about it.
She won't allow that.
But yeah, this one lives in the lounge. It's a nice, you know,
It's a beautiful piece to have.
it's a nice, yeah, talking point as well. You know, I think we've had a few people in. You know, we had some new windows fitted not that long ago, and some carpets as well. And you know, first thing, what's that? What's that? And you know, so yeah, good talking point. But
So
yeah,
how many hours do you think you put into that?
what, and the mirror as well?
Yeah.
Everything.
Yeah.
I wish I'd recorded it, you know. It's got to be, I don't know, 1,500, something like that. 2,000 hours maybe. I don't know. It's a lot.
A year's work.
It's a lot. I mean, I was working on it quite a few evenings after work and most weekends. Yeah, it was a lot of work, but really satisfying. You know, it's you know, I could have gone out and brought 10-inch dobsonian, but you know, there's nothing like, I don't know, there's just something about being able to sort of look at those objects with something, you know, especially the mirror. You know, it will, even if I think if I built all this and then bought the mirror, I don't think it would give me quite the same satisfaction. You know, because obviously the mirror as well, you know, that's the magic happens. Yeah. So
What's your mirror made out of?
it's same as that blank. It's a 10-inch borosilicate, so it's a low expansion, similar to Pyrex. That's what we call borosilicate glass, and yeah, it's a low expansion glass basically. Yeah, mirror making is a whole other thing to learn altogether, but great fun, really enjoyed it, especially the testing the mirror optics. You know, literally bench testing it using light to test the mirror is and again, that, you know, those tests are very sensitive. I mean, you know, I work in the aerospace industry, and when I talk to the guys at work, you know, about tolerances, I mean, we're talking on aircraft, you know, tolerances maybe down to sort of 0.1 of a millimeter. On here, on a mirror, 0.1 of a millimeter is just nowhere. We're talking nanometers. You know, we literally, the surface of a figured mirror is extremely accurate.
So it's not visual. So how do you know that you're sort of in the ballpark? How do you know that you're going the right direction?
Bench testing when you're grinding the mirror, yeah. Well, especially when you get to the figuring stage. So there's what they call the grinding stage, is where you remove the bulk of the glass, and you take it down to a spherical shape. It's actually a sphere, and then once you've polished it, you then polish it, and then once you've got a polished surface, you then final figure it, which takes it to a parabola, and a parabola will actually then focus light all at the same point. A sphere won't. You get what you call spherical aberration, where it actually focuses slightly different points from the edge as you go in towards the center, whereas you have to deepen the center very, very slightly and then figure it. But the figuring is the trickiest part, and that's the bit you have to test and make sure you get a really good figure, because that's the only way you're going to get a nice sharp image. And you can actually, you know, with simple, well, fairly simple testing at home, you can actually look at the surface figure and actually measure the surface figure, and it'll tell you the accuracy of the surface. So when you hear people, you know, they talk about their mirror accuracy, what wave, you know, you've heard of people say, I don't know, they measure it in wavelengths of light, the actual distortions. So you know, I think it's diffraction limited is a quarter wavelength of light maximum wavefront error on a mirror. So a quarter of a wavefront of light is incredibly small, because the wavelength of light is, you know, measured in nanometers, I think it is. So yeah, and I mean, the mirror I did tested as it's about 1/20th of a wavelength.
Pretty good.
I mean, that was just purely just keep going and going and going, test, go back out, test, rub, polish. And literally, when you get to figure and you're using polishing techniques, you're polishing the surface of the glass. You're taking off such small amounts, but yeah, polish, test, keep in and out, just keep test, doing that for quite a long time until you've, you know, I mean, beyond that, you really, I mean, you know, people, I mean, expert mirror makers like Gordon Waite in the USA, they'll figure 1/30th wave mirrors, but really you'd be really hard pushed to see the difference between a 1/20th wave, in a 1/10th wave mirror and a 1/30th. You'd need extremely good seeing conditions. I mean, the chances of getting that in here are very, very unlikely. I mean, but yeah, it's all in all, you know, I'd say very, very satisfying, especially when you can start taking some images. Yeah, so
Well done.
Excellent.
So that was an adventure.
yeah.
Oh.
Do you detach the fine adjustments? No, to just move it
No,
around?
No, you can move it. I mean, fairly gently, but if I show you, you know, you can move it.
Oh, wow.
Okay.
See?
Knobs.
Yeah, okay.
And then obviously you've got the fine adjustment. So you can move it very, very slightly for tracking it by hand.
Okay.
So you just watch the image, did you?
Yeah, on the screen,
yeah.
and you just track it,
And just
just
track
keep it in position.
Can I have the other?
Yeah,
What do you want?
you just lift it, carefully here.
Yeah, that's pretty good, isn't it?
There is a little bit, I mean, the universal joints have a little bit of play, can't get around that, but this one doesn't at all,
Yeah.
really. But you can feel if you go down slightly lower, you know, you've got a good stiction there. So like I say, when you get the
Chris, Sandy, Roger, do you have any questions?
I presume the primary mirror is silvered or aluminized.
it will be. Those
So how will that be done?
not by me. I'm not going to do that myself. I'm going to get that done professionally. But yeah, those images actually were taken with the unsilvered
Seriously?
mirror.
Really?
Yeah,
Amazing.
yeah,
Or just the glass?
yeah. Straight off the glass.
Yeah, that's amazing.
Yeah, not as obviously when you look at it visually, I mean,
Yeah.
it still looks great. Not as bright as it would be if you have it silvered.
Yeah.
Obviously, you're losing quite a lot of light through the glass,
Yeah.
but the you know, still enough off the moon to be able to take
Just get some
some.
funny reflections back to store the whole image.
No,
Right.
no,
It's a new idea.
but yeah, so I mean, I haven't sent it even yet, so it's something. It's the next thing I've got to do. But obviously, with all the, you know, things going on with coronavirus and all that,
Yeah.
I've just not got around to doing it. So
Trust them
I'm-
to do it.
that's the thing. I mean, I'm literally going to take it there. I don't trust the courier to take it.
No.
I'm going to drive it there, hand it over, wait, hopefully, and
Where-
bring it
where-
back.
Where is that?
Well, you've got there's a couple of places. Orion Optics UK do them. There's Vacuum Coatings, which is actually in Battersea, I think it is.
I take the mirror there and bring it back.
Yeah. There's also another place, I forget the name of it at the moment. I think, but this other, can't think of the name of them, but this other place isn't as well known, but looking at their website, they do some pretty big stuff, you know, like serious big professional sort of mirrors. But I did get a quote off them, and they were quite a lot more expensive. So I'm not sure which way I'm going to go yet, but having put all the labour of love into it, I don't want to cut any corners at the end. Hopefully, that 1/20th wave that I sweat blood over to get, I want to keep once it's been silvered. So, you don't want any sort of uneven coatings going on.
What's the actual thickness of the coating?
It's microns, it's only microns. It's not much at all, really. It's like I say, it's like gas deposition in the vacuum chamber. Just a very, very thin coating, but yeah, even is the most important.
So if Pete goes into business making telescopes, who wants one?
Okay.
Well,
This is a full year's work.
I think I can
This-
How much do you charge?
afford you, yeah.
I mean, my plan is to retire in 2 years from Airbus.
Yeah.
So, that's, I know I've considered, doing mirrors, not so much the whole scope, but certainly mirrors, because not many people do that. I can't think there's that many, and maybe there's a market out there for that sort of, standard of optic.
Well, it certainly is, yes.
How about making specular mirrors? As you're working with metal?
Yeah, there's certain processes overlap. But yeah, we discussed it, didn't we, about a while back. But
There's a guy who came here, a crazy
yeah.
American, who was a biologist by training, and he was a metallurgist as a hobby. And he's got part way towards making some specular mirrors for us, but
He's disappeared.
he disappeared, sadly, yes.
I should have my mask on, shouldn't I, really? Yeah, sorry, forgot again.
Is there any advantage to that?
None at all. It's just been like history.
Right, yeah, okay.
Yep, you're missing a beautiful looking telescope, Chris, Sandy, Angela, and Roger. Oh, we've lost Angela. Okay.
It's the kind of thing that a non-astronomical household would be happier to have in his living room
Yeah.
than,
Well, like I say,
normal thing.
yeah. That was, what I was saying, really. I wanted it to look aesthetically pleasing as well.
It really is a work of art.
We've seen the Oxford stuff.
Yeah.
Thank you.
This all brass.
Yeah, okay, really?
He did a ceremonial one presentation to Japan.
Okay.
But, yeah, I actually saw one of these I was down the Isle of Wight doing a bat survey with people who've got this fantastic set of brass binoculars on them.
I don't know if
There's a market for all these things.
Oh,
There's a market.
I don't know if I can turn it round.
It needs to be aesthetically artistic.
Yeah.
If you want to make it worthwhile,
Yeah.
it's just trying to compete. So like, here's a nicely made telescope. It's never gonna. Yeah.
Let's go see because you were asking about the fan and the little
Oh, yeah.
battery. I don't know if it will go
I can
down.
see the mountains up here, but
So there's a little
Power bank.
power bank there,
Yes.
which is probably flat now because I'm used to it. But yeah, a little switch on the fan, and then that just cools, and there's yeah.
So when you disassemble it to carry it, is this going to be a lift-off job?
Yeah, it just lifts off. It's quite heavy, like I said.
Yeah.
And do you disassemble it to carry it around this?
Well, just yeah.
Oh, the dust is off.
Yeah, the truck obviously that all come off, but what I did, I didn't actually explore another little mod that I did because I see people, fiddling around with the truss rods and they're real problems. They're all flailing around trying to get them in. So I tried to leave them in this end, and I 3D printed these little mounts, and there's some little rubber O-rings either side that just stop that moving.
Okay.
So when I unbolt these here, it pretty much holds it,
Okay.
and so I can then just
Take it off.
take it off and on quite easily. without those, these rods tend to sort of, it's a bit more of a, you know,
It's
much
much nicer
mirror,
getting-
isn't it? For have bits of metal flame.
yeah, yeah, but
I
yeah.
try to avoid taking mine apart.
But no, I mean, I tend to, that cover always stays on really until I've put everything on. It's the last thing, it's the last thing to come off. Like I say, that's just a blank. That's just a plain flat piece of glass. But yeah, you got to be careful with the mirror. And this was another little mod as well. It was the finder scope. It was just a little mirror, 3D printed little bracket. So I can look, just so much easier to look like that than to look like that, to cranking your neck all the time. Yeah, so that little mirror there, God, that makes such a difference. You know, you can look like that, see the little red dot finder, and yeah, much nicer. You know, so it's trying to make it as, you know, you try to make it as a pleasant experience as you can, don't you? You're out observing or imaging or whatever. But yeah.
Yes, if we're using one actually for normal visual observing, you wouldn't want to have a finder scope on there. So you know you've got that weight to get rid of too.
Yeah.
And they've got that there 60 mil, which is a fair weight on mine.
Yeah. Well, this one weighs next to nothing.
Yeah, sure.
It's literally probably 100 to 150 grams, I would think.
Trying to find the movement, trying to find the setting.
Yeah. Yeah.
Okay, I'd like to thank you, Pete,
Yes,
for a wonderful talk.
That's okay.
Really incredible. It's so impressive.
Thank you.
And
Thank
showing
you.
your telescope and actually how you built it piece by piece and what a challenge it was.
It was a challenge.
Yeah.
Yeah.
And to be able to do both the design and the building is
Yeah.
quite an undertaking.
Yeah.
Usually you get people who are good at one, not the other. So,
Yeah. Thank you. Thank you very much.
And people have said your wife is a saint. I think this proves it.
Yeah. 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 It's you know, spent a lot of time out in the workshop and yeah, an understanding wife. But yeah.
I'm thinking about stealing it, but I don't think I'm going to get it home on
Yeah. It literally just.
Bringing that on here.
the bus. It doesn't go to the stairs.
Okay, well, so I'd like to thank everyone for coming along. I hope you enjoyed it. We've got our session next month with Lucy Green, which will play out similarly, but instead of having all the cameras and things like that, it's all. I think we'll actually have a camera coming back towards the audience, so she gets to see us all. And things will have a slightly different configuration, but just a month's time, and we'll have that session as well. Thank you for all those that joined us remotely. We still love you. And I hope to see you in some of our observing events and items like that going forward. That would be great. Oh, I'm being given bits of telescopes whilst we speak. So thank you, everyone, and enjoy the observing in October, and hope to see you out stargazing.